Happy Eclipse Day, everyone. On the stream, we'll be highlighting all the NSF-supported science that will be going on across the country during today's eclipse. We'll learn about the impact from space weather, talk to experts, check in on field observations, and visit the world's most powerful solar telescope. Stick around. Thank you for joining us. From the National Science Foundation, I'm Adam Eggers.
And with the National Solar Observatory, I'm Jorge Perez Gallego.
We have a ton of stuff we're packing in, learning about our closest star and what experiments we'll be running today.
And we will be checking with the path of totality in Dallas, Texas, with solar physicists Ryan French and Kevin Reardon.
Now, Jorge, as the astronomer, would you be able to explain to us some of the different things that are going on in the layers of the sun?
You got it.
Since today is all about the sun, and I know we have some classrooms tuning in, I think it's probably best if we start from the beginning.
Our sun is a star. Like the many you see up in the sky at night, it is just way closer than those. Just 8.3 light minutes away, or about 93 million miles. The sun is a 4.5 billion year old yellow dwarf star with surface temperatures of about 5,000 to 6,000 degrees Kelvin. That's about 10,000 degrees Fahrenheit. It is an ordinary star, one of about 100 billion stars in our own galaxy, the Milky Way. The sun is at the center of our solar system, and it is its gravity that holds the solar system together. The sun is arguably the main influence on Earth and essential to life as we understand it. Because of our long, strong, and vital relationship with it, and how it represents a stepping stone in our pursuit of knowledge, it is crucial that we research the sun. But what do we know about the sun structure today? Well, the energy of the sun is generated at its core, where it reaches temperatures of 15 million degrees Kelvin. This is by a mechanism known as nuclear fusion, where hydrogen becomes helium as energy is being released. This energy moves then through the interior of the sun, being absorbed and re-radiated, converting high-energy gamma rays to less energetic photons in the radiation zone. Plasma then becomes turbulent in the convection zone, where hotter rises and colder sinks like water boiling in our stoves. Energy then continues to work its way out through the photosphere, the visible surface of the sun. The photosphere is marked by bubbling, bright granules of plasma and cooler, darker sunspots, which emerge when the sun's magnetic field breaks through the surface. Above the photosphere, we have the chromosphere and the corona, which stretches 5 million miles above it. What's puzzling is that while the sun's surface is about 5,800 degrees Kelvin, the corona reaches temperatures of about 1 million Kelvin. Figuring out what heats up the low-density corona is an active and crucial area of research today, and key to understanding how heat and energy are transferred into the solar wind, a constant stream of particles blasting into space away from the sun in all directions, including ours. However, seeing the corona from the ground is an uttermost challenge. The extreme brightness of the solar surface overwhelms any coronal light, needing innovative solutions to see through the glare, like those at the U.S. National Science Foundation Daniel K. Inouye Solar Telescope, or a total solar eclipse, like today.
Hey, Jorge, how do we know the different layers of the sun?
That's a great question, and what we've done through history is use human ingenuity to interrogate our sun. We've built telescopes and observatories to measure different properties that collectively have given us the picture that we have today. Telescopes like the Daniel K. Inouye Solar Telescope in Maui, or observatories like the Global Oscillations Network Group all over the world that allow us to look at the sun constantly during a whole day. Those are just some examples, but we keep pushing the boundaries to try to get a better idea of the sun's behavior.
Awesome, thank you. Understanding the sun is a pretty big deal. Life on Earth is critically dependent on the sun, and it's important for us to understand and hopefully predict the behavior of our dynamic star. A new tool in this endeavor that Jorge just mentioned is the Daniel K. Inouye Solar Telescope in Hawaii, the largest and most powerful of its kind in the world. Check it out.
The Inouye Solar Telescope is on Haleakala, on the island of Maui, and this site was picked because it offers the best conditions for solar observations. And those conditions are low atmospheric turbulence, so we get very clear images of the sun, but also low scattered light in the atmosphere, so pollution is very low. Aerosols are very low.
One of the big distinctions between ground-based telescopes and ones in the sky is that we actually have to look through the atmosphere. The atmosphere is something that protects human beings here on Earth, but it also can cause turbulence, more or less, in the optical beam that the telescope will see. Not only do we want to get really good images of the sun, we also want to understand the magnetic field properties. And so what polarimetry can provide is an ability to see the magnetic fields.
When we open up the telescope, we actually open a 4-meter hole in the enclosure, and the enclosure points towards the sun. So that's how the solar light enters into the telescope facility. And the first surface the solar light hits is the primary mirror.
There's a whole optical path that folds the light down through to the telescope into the coude, which is where the instruments are.
Once that light comes down from above to the laboratory, what happens is that image starts to rotate. Because you're trying to track the sun, but the image of the sun is constantly rotating. So for our scientists who really want to study a feature on the sun, we don't want that small magnified feature to be rotating as they're taking their science data. So the coude lab actually provides a way to counter-rotate that rotation.
We analyze the sunlight in different ways using those different instruments. Imagers give us a movie view of what is going on the sun, and the polarimeters and spectrographs give us more physical information about what is going on in the sun.
And then the solar light, which is white, gets through, call it a big prism or big prisms.
And it spreads that light out into the solar rainbow and looks at very specific snippets from the spectrum at individual colors of light, and it does the analysis there.
And so a number of instruments do this. They actually will change the orientation of this grating, as well as change where the cameras are located in order to see the different colors of light.
And the data from all these instruments, which are working simultaneously, is then combined to get the maximum understanding, the maximum information about the solar magnetic field and solar structures. So the future, I think, will bring a lot of new results, a lot of new things that we learn about the sun with the instruments that we currently have. We're already working on new instrumentation, upgrading instrumentation, so it really is a continuous effort to improve and stay up with technology. It is exciting and will continue to be.
This year's eclipse brings a unique opportunity for further testing of the sun's corona. To hear more about his NSF-supported research, here's Tom Shad.
The sun is important to study for multiple reasons. One of the biggest reasons, of course, is that it's the giver of life for Earth. Everything that we do on Earth, energy-wise, is somehow derived from the sun. So the connection of the sun to the Earth is the first driving principle behind what we do. We have a very broad science mission. We focus on the tiniest details of the solar surface because a lot of the energy content that drives things in the atmosphere of the sun, which is then connected with everything around Earth and in the inner heliosphere, everything kind of is coupled at a large range of scales. Things that are very tiny can actually play a very large role even on big scales. So with the telescope, I study things that range from the tiniest of features at the surface layer of the sun to things that are much larger, almost Earth size or multiple Earth sizes up in the upper atmosphere in the corona. So with the telescope here, we can study a large range of solar science and how it connects to the inner solar system. Eclipses are really prized moments for solar physics. Now, because of that special condition of a solar eclipse, even though it's short, it's 2 to 6 minutes, you can deploy so many different types of experiments to take advantage of those conditions. So they're really rallying calls to do science. So here at Inouye Solar Telescope, we'll be running an experiment using our fake eclipse, our coronagraph. But this is being orchestrated together with a number of experiments that's across the eclipse totality path. So we've been talking with teams in Texas and Mexico and throughout central US, talking about the types of experiments that they're running to take advantage of this pristine time, and then trying to best complement that with the advances that we have here at our telescope.
The Inouye is part of the NSF-supported National Solar Observatory, where Jorge is the head of education, public outreach, and communications. For the people not familiar with NSO, can you give us an overview?
Of course. The mission of the NSF National Solar Observatory, or NSO, is to advance our collective knowledge of the Sun as both an astronomical object and the dominant external influence on our planet, by providing forefront observational opportunities to the research community. This mission includes the operation of cutting-edge facilities such as the US NSF Daniel K Inouye Solar Telescope and the Global Oscillation Network Group, the continued development of advanced astronomical instrumentation, the conduction of pioneering solar research, and the implementation of innovative education, public outreach, and communications efforts for broader audiences. NSO operates, as we mentioned, the Daniel K Inouye Solar Telescope on the island of Maui, Hawaii. At 4 meters wide, it is the largest solar telescope in the world. With a focus on understanding the Sun's explosive behavior, observations of magnetic fields are at the forefront of this innovative telescope. NSO also operates the Global Oscillation Network Group, or GONG. Deployed in 1995, GONG is a set of 6 observing stations geographically distributed around the Earth so that the Sun can be observed as continuously as possible. The 6 locations are California, Hawaii, Australia, India, Spain, and Chile. With these sites, GONG typically can observe the Sun 91% of the time. GONG was constructed to provide observations for what we call helioseismology, which aims to understand the solar interior by analyzing the sound waves that are trapped in it. GONG datasets are used for research into the solar magnetic field and chromosphere, but are also essential inputs into forecasts of space weather. Many federal agencies actually use GONG data to predict space weather conditions.
Dr. Carrie Black is NSF's Program Director for the National Solar Observatory, the Inouye Solar Telescope, and oversees our solar astrophysics grants portfolio. We sat down with her to learn more about the impact from space weather on Earth.
So space weather starts with the sun. The sun is always emitting material, solar wind, plasmas, and it sets it off throughout the solar system, and that's sort of the background for space weather. But we get things like storms. Coronal mass ejections are big solar eruptions, and they have lots of material. It's really important to understand it a lot today, like in today's society, because we have so much that depends on electricity. Our electrical grids, our satellites, our communication satellites, all of these things can be impacted by these big solar eruptions. The particles, when they hit Earth's upper atmosphere, can cause the atmosphere to sort of to grow a bit. And because the particles are so energetic, when those things hit satellites, they can be disruptive to satellites, cause charging on the surface. So understanding the solar environment, the atmosphere, the background, what's happening there, and then when you have storms erupt is really important for monitoring these systems because these systems can be so disrupted. So it's a lot of stuff that we don't necessarily see on a day-to-day basis, but is important to understand in the long run because they are electromagnetic storms essentially. So when you get buffeted by something like a coronal mass ejection, it can disrupt them, it can cause large electrical currents to run through our power grids and potentially be destructive there as well. Solar eclipse is an amazing time to study the sun because we are positioned sort of perfectly, and the moon is positioned perfectly to block out the very bright disk of the sun so that you can see the corona, which is the solar atmosphere. It's very diffuse. The surface of the sun is so bright. When you look up in the sky, you just see this bright ball. And so it's so bright that you can't see what's happening in the atmosphere, in the corona. So under normal conditions, you won't really be able to see the corona. You have to have something blocking out the surface. The most exciting thing for me about space weather is the day-to-day changes. It's really cool to be able to look at the sun and track a sunspot that you see growing or changing in complexity and try to guess if it's going to erupt. And this is something anybody can do. You don't have to be a scientist to be able to do this. I really like monitoring features like filaments, which are these long magnetic structures that can grow on the sun and they can erupt too. So it's fun. It's fun because it's dynamic. On a day-to-day basis, it's fun because it's always changing.
We'll put a link to our full segment with Carrie in the description. And while sunspots are pretty cool, like she said, they actually are literally cooler than the surrounding area. These dark spots are a sign of concentrated magnetic fields. So let's talk to solar physicist and your NSO colleague, Maria Kazachenko.
Hi Maria, here's a question. Can sunspots and space weather be predicted?
That's an excellent question. So we know now from historical records that the sun has this 11-year cycle, meaning that every 11 years now there is a maximum and then a minimum, a maximum and a minimum. The next maximum will be sometime from now till 2025. So now we are in solar maximum. So there are lots of these sunspots. Now, why this cycle is 11 years and not 42 years? We don't know.
Is it actually possible to predict how large a sunspot will be?
That's a tricky one. So that's why basically the whole field of solar physics and people like me have their jobs. It is extremely hard to predict how large will the next flare be. Now, we know some things that, for example, big sunspots, they're more prone to host big flares than smaller sunspots. But solar physics, it's still at its birth. I would say it's like geography in the 16th century. We have lots of observations from this wonderful telescope from NSF, but we still don't understand how big the flare would be. Will it be very small or it will be huge? Will it erupt or will it stay at the sun? These questions are fundamental, and yet we have not enough knowledge to understand them.
Let me ask you, why is it important to study the sun?
That's an excellent question. So let's think about it a little bit. What are the building blocks of our universe? These are stars, right? And sun is our closest star. And as a closest star, that's one of the reasons we want to learn everything about it. So just from the fundamental science perspective, we need to understand the building blocks of the universe. We are made out of byproducts of stars. So it's important also to understand ourselves and the stars.
Another NSF-supported plasma physicist is Alan Brizard, who joins us to talk about the star we all share.
It is fascinating that the closest star to us still has many mysteries that need to be solved, that are crying for a solution. We still don't understand why the solar corona is so hot. So this is just a perfect opportunity for the general public to observe this last mystery associated with the sun. I think it's fascinating that the sun presents us with enough scientific information to build models of the universe, but still keeps some secrets, some mysteries that are absolutely fascinating. You know, there is a sense in this modern society that is so surrounded with technology and science that there's nothing else to discover. And yet, we will be looking at something that is filled with mysteries. Still, instead of looking at a screen, totally being oblivious of each other, will hopefully be looking at the sun with solar eclipse glasses. And we're all, as a community, observing a once-in-a-lifetime event. You know, it's as if, you could ask, where were you on April 8th? People who are witnessing this event will say, yes, I know exactly where I was.
Now that we know about how space weather impacts Earth and saw one of the major telescopes we use to study the sun, Jorge, can you tell me a little bit more about the science that will be going on during today's total solar eclipse?
Sure thing, Adam. First, experience has shown that the beauty, rarity, and brevity of a total solar eclipse always produces significant public interest and excitement. Besides that, there is also a scientific interest because of the rare access we get to the corona from the ground. 3 key scientific observing programs I can talk about are CATE 2024, Super CATE, and at the Daniel K. Inouye Solar Telescope atop Maui's Haleakala. CATE 2024 is led by Amir Kaspi, who will join us in a few minutes. Super CATE is led by NSF scientist Kevin Riordan, who we also be speaking with shortly from the Path of Totality. And finally, the Daniel K. Inouye Solar Telescope is using spectral lines of highly ionized atoms to map coronal density and magnetic fields. These data will be then compared with the data of CATE 2024 and Super CATE. And finally, the measurements can be also compared to in situ data from the Solar Space Telescope's Solar Orbiter and Parker Solar Probe.
Another of the observations today is called ACES, which will attempt to chase the eclipse in an aircraft. Seriously. Astrophysicist Lisa Winters tells us more about the project.
It's really important to understand what's going on in the sun because the sun is basically what allows us to be here on the Earth. It provides all the energy for plants, for the atmosphere to be here, for everything. It also is not constant. We think of the sun as always being the same, but the sun goes through these phases and activity cycles. Last solar eclipse was in 2017 that we could see in the US. That was during solar minimum. This time it's during solar maximum, which is when all of these flares and CMEs are driving space weather. ACES is the Advanced Coronal Emission Surveyor, and it's a really cool new instrument that was developed by Jenna Samra and her team at the Smithsonian Astrophysical Observatory, where they're working with NCAR to put this new instrument on an airplane and chase the solar eclipse to observe the solar corona. It is designed to be a spectrograph that will observe the sun in the near infrared. In those wavelengths, we can understand the temperatures and densities of the hot plasma in the solar corona in the inner part of the corona, which is a part of the sun that we can't observe unless there's a solar eclipse. When you are observing on the plane, you are above a lot of the clouds which emit in the near infrared, so they're able to be above a lot of that layer. They're going to be above any clouds that might block out the sun if you were on the ground. If you just stood in one place during the solar eclipse, you would only get to see the eclipse for 3 to 4 minutes, but because they're on an airplane, they're actually chasing the shadow of the moon, so they're going to get a full 6 minutes to observe. The outer layer of the sun, it's millions of degrees, and we don't know why still, so it's a big mystery. We know that the surface of the sun is about 6,000 degrees Kelvin, but somehow between the surface and this outer layer are heating up to over a million degrees. So it's very, very basic physics that we just don't understand yet. So the ACES team, by studying the solar corona during the eclipse, will be able to get more insight into this. And the corona is where a lot of what launches space weather towards us happens. So understanding Any bit of that process can help us also to forecast when a solar flare will happen, when space weather effects will be felt here on Earth.
One way communities are getting involved with solar science during this total eclipse is through a program called the Citizen Continental America Telescopic Eclipse 2024 Experiment. We're joined by Amir Caspi, a solar physicist at the Southwest Research Institute, who is managing the program.
It's my pleasure to be here. Thank you so much for inviting me.
Good afternoon, Amir. Tell us about KATE 2024.
So we have an experiment called Citizen KATE 2024, and this is a large participatory science, or sometimes you might hear it called citizen science experiment, that will deploy 35 teams of volunteers all along the eclipse path for the total solar eclipse that's coming up, from Eagle Pass, Texas to Holton, Maine, and everywhere in between. And we have provided our volunteer teams with cameras, computers, telescopes, mounts, all of the necessary equipment that they need to make the observations that we need for science. We've given them training on how to make those observations. And as the eclipse shadow passes over land from Texas to Maine, we're going to get about an hour-long movie of totality from our community volunteers.
Amir, what is unique about KATE 2024?
So there are two main novelties in our project. The first is our science. We are observing the sun, the solar corona specifically, in polarized visible light. Now, not everybody's familiar with polarization, or at least not in a scientific sense. So let me explain it a little bit. Light is a wave. Hopefully everybody knows that. And, it kind of waves like waves on a string. And waves on a string, they go up and down or left and right. And so that up and down is what we call the polarization angle. And so in the solar corona, when you're looking at that eclipse with your eyes, the light that you see, most of it is not actually coming from the corona. It's actually coming from the solar surface, and it's sort of going out into the corona, interacting with the particles in the corona, and then scattering, bouncing into your eyes. And that process makes the light polarized. So with KATE 2024, our cameras are actually special cameras where every single pixel of the camera has a little polarization filter on it that measures a particular angle of polarization and allows us to measure structures in the corona and dynamics in the corona in ways that you just can't do any other way. The second really cool novelty with this is that this is a distributed network of amateurs. We are not employing, professional scientists to make these observations. These are students. These are youth groups. They're teachers and other educators, retirees, people who are not professional scientists or certainly not professional astronomers. And they're making these observations for a scientific project. Some of these folks have never touched a telescope in their life before this particular project. And one of our main goals is to really highlight how eclipses can be a transformative experience. Science is for everyone. Eclipses especially are for everyone. And you don't have to be a PhD scientist to do science. You don't have to have ever touched a telescope to contribute to astronomy. And hopefully this experience will be transformative and transformational for our participants in such a way that they leave this not just having seen an eclipse, but having felt that they really meaningfully contributed. And who knows? Maybe that's going to shape the rest of their lives.
And tell me, why is citizen science so important?
Why is citizen science important? Well, science is not just for people who have gone and spent, 80 bajillion years in school. You can be a scientist as a kid. You can, in fact, a lot of kids are scientists without even knowing it. By playing around with things, they're experimenting, they're learning about their world around them. Everyone can do science. Everyone really is a scientist at heart. Everyone likes to see what happens if I do this thing and what happens if I don't do that thing. And there are also lots of other jobs and other skill sets that are required to help live in a scientific society and to help support science. Art. people think art is divorced from science. No, I mean, art is really important in science because we have to find ways of visualizing our data, put my data together in a way that makes sense for me as a visual human being absorbing stuff. I'm not a computer. Ones and zeros or even just a string of numbers doesn't make a lot of sense. How do I make a graph, a chart, a picture, an image that means something to me and my brain can process and understand what that means? So citizen science, participatory science, it gives people that experience that they might not have, especially if they're in a community that might not have access to a lot of resources. There are lots of people who could become great scientists if only they had the resources and the mentorship at a young age. And we're trying to break down those barriers. We're trying to give those experiences and resources to however few people we can do it to, and hopefully break down silos and really encourage people to get an appreciation for science. Even if they don't become scientists, they know that they live in a scientific society and that they support scientific endeavors.
Thank you so much, Amir. And now a message from the director of the U.S. National Science Foundation, Dr. Sethuraman Panchanathan.
At NSF, we are all excited to witness and study one of nature's most incredible displays, a total solar eclipse. It's a tremendous opportunity for all of us to be a part of exploring the mysteries of the universe, to become citizen scientists. But just like any field work or experiment, it is essential that we practice safety first. Even during an eclipse, the sun's powerful rays are too strong for our eyes to look at it directly. Staring at the sun at any point other than total eclipse could cause eye damage and even blindness. That's why you must be sure to wear approved safety glasses like these. Look for the label ISO 12312-2 so you know that the glasses are properly rated to protect your eyes from the sun's radiation. I hope you will join all of us at NSF to safely celebrate and investigate this great natural wonder.
Now that we're set for safety with Eclipse glasses, let's check on some of our live camera feeds. We'll go to the control room at the Inouye Solar Telescope in Hawaii, and then to solar physicist Kevin Reardon, who's in Carbondale, Illinois, with his 2 telescope setup that includes his SuperCate setup.
But first, let's check with Ryan French in Dallas, Texas.
You're about to hear the crowd go crazy. We're here at the Pro Museum. The sky has gone gray. We have blue skies. It was cloudy earlier. We can talk about that. You're about to hear a lot of excitement. I'm about to look up myself and enjoy this. Wow. Instant chills. Instant chills. There's not a cloud in the middle of the sky. I can see a couple of planets popping up here. That's Jupiter and Venus. I'm seeing a lot happening right now. This is the diamond ring. Maybe we can talk about that afterwards. Wow. Okay. Hopefully you can probably hear that around me. You can probably see it's gone very, very dark very, very quickly. This is actually very, very emotional. Wow. Oh my goodness. I am speechless. I think we're going to see a few... I can barely talk. I'm sorry. We're going to see a little panoramic, a few shots either side of me here at the crowd. That, in one word, that is magic. I am honestly stuck somewhere between being speechless and wanting to incoherently babble at you for the next 3 minutes. Wow. Okay, it is dark. The city lights in Dallas have come on around me. Goodness, and I can see the corona, the atmosphere of the sun, with my eyes. This is truly a very, very special thing that I'm seeing right now. You might notice I have this very janky telescope set up next to me. I'm going to attempt, while I'm talking to you, to see if I can get a shot or two of the corona right now. That might not work out so well, but my goodness, I think we're just going to sit here in quiet for the next minute or so. Yeah, enjoy listening to the screams around me if you can hear them. And I think we're going to pan around one more time to get another view of the crowd here at the Pro Museum.
So if you look out about 5 o'clock on the face of the sun, there's a bright dot towards the bottom. I think that's a solar flare that you can see coming down. And we have less than a minute of totality left. Your glasses ready. All right, so people should start putting those glasses back on. We've only got a few seconds left, so put those glasses back on. And we'll see the diamond ring come out the other side. There we go!
Wow.
All right, keep those glasses on. You can keep watching the partial eclipse.
You still hear me there in the studio?
Yes, Ryan. So can you describe the vibe there right now?
Well, hey, I'm speechless. Let me tell you this. I have been researching the sun as a profession since 2017. I've written a book on the sun. I understand the atmosphere of the sun. I understand eclipses as well as anyone, but that is the first time in my life I have seen the atmosphere of the sun with my own eyes. I just feel like I'm somewhere between tears and wanting to scream with joy. I'll keep it professional for you guys there. But you may have heard, you may not have heard. I don't know how much audio you could pick up. There were screams, there were gasps. That might have been one of the best experiences of my life. And I say that in front of my wife, who we got married a year and a half ago. A close second to my marriage, I'd say. But that definitely, absolutely surreal. Wow. And I think we've got a few minutes now to answer some questions before you see totality through the telescopes that we have set up a few hundred miles north in Carbondale, Illinois.
Thank you, Ryan. So let's talk a little bit about it. So what can scientists measure during a total eclipse that they cannot measure in other circumstances?
So the key thing that we can see in an eclipse is the atmosphere of the sun, the corona. The sun has an atmosphere, and you can't see it in the daytime sky because the sun, the surface of the sun is too bright, the blue sky is too bright, so ordinarily we can't see it. But during a total eclipse, the moon blocks the main body of the sun for us, so we can see that atmosphere of the sun. So we can measure that with telescopes on the ground, special scientific instruments. You'll notice, although you're seeing some telescopes on your screen intermittently, there are no telescopes around me right now. The original plan was for Kevin Reardon and his team to be here with the telescopes that you're seeing and to sync up totality. But the weather here in Dallas, very, very uncertain the last week, flip-flopping between a forecast of cloud, clear skies. Even this morning, 3 hours ago, I didn't think I was going to see an eclipse today. Even 30 minutes ago, 20 minutes ago, I wasn't sure I was going to see the atmosphere of the sun, but it cleared up beautifully. So for that reason, Kevin and his team, they're further along the path, and we'll see their view coming in intermittently until totality up there in Carbondale.
So what are some of the tools that scientists use during eclipses?
So we have a whole range of tools. I think you've learned about a few of them. We have cutting-edge telescopes here on the ground, such as the Inouye Solar Telescope we heard from earlier. We have telescopes in space that are observing the sun from different vantage points. And then here in the path of totality, we have flights flying along, measuring the corona of the sun. But the key thing that a lot of these instruments are measuring isn't a photograph of the eclipse itself, but it comes down to measuring the spectrum of light. By measuring what sort of colors of light the sun is absorbing and emitting, we can learn a lot about the atmosphere of the sun, and that's the science that is mainly being done today.
So let me ask you, what are some of the most amazing eclipse expeditions or observations that you are aware of?
Yeah, so there's a lot of cool science going on today for this eclipse, but probably the most famous one of all time dates back to the eclipse in 1919. There's a very famous scientist everyone will have heard of, Albert Einstein. He came up with a wacky theory called the theory of relativity, saying that large objects in space can bend sunlight. And during the 1919 eclipse, a man called Edison and a bunch of astronomers, they went on an expedition, and during a total solar eclipse, they measured the position of stars had been warped slightly by the gravity of the sun. And so they proved that during that eclipse, Einstein was right, and general relativity is the universe that we live in.
Okay. Ryan, so how has technology helped make eclipse observations easier? What are key aspects that you might consider that are allowing us to study the sun the way we're studying it today?
Sorry, we've got some loud music just started. Could you repeat that question one more time?
Yeah, like can you give a couple of examples of technology that has helped us make these sort of observations easier through time?
Sorry, Jorge, I'm really struggling with the audio. One more time here.
Okay, can you comment on technology that has helped us make these sort of observations easier? Yes, technology.
With you. Yeah, so I'm going to go out of field here and say the best technology is nothing to do with the sun, it's weather forecasting. So, as we mentioned earlier, our team of scientists here on the ground doing some fun experiments in the form of Supercape, they're not here in Dallas, where we have been predicted cloud for a long time. They are up north in clear skies. So with the technology of accurate meteorological forecasting, we're able to get the experiments to where they need to be, where the corona is going to poke out from between the clouds.
Okay, and can eclipses tell us anything about the Earth's atmosphere?
They certainly can. So as we all felt here in Dallas, during that total solar eclipse, it went cold, it went dark. Now, the upper layer of the Earth's atmosphere, it's called the ionosphere, it interacts with sunlight all the time. And by measuring how the upper atmosphere changes during a total solar eclipse, scientists can begin to understand our own planet as well as just the physics going on the sun as well.
And let me ask you also, I should have asked you this earlier, but what is unique about these eclipses? What kind of things are unique about these eclipses?
So there's a few key things going on with this eclipse. The last time the United States saw an eclipse was in 2017. This eclipse, in contrast, is being seen by about 2.5 times more people along that path of totality. The eclipse is longer, over twice as long, and this eclipse is happening at a special time as well. We call it solar maximum. We're currently in a phase where the sun is very active, a lot of flares, a lot of eruptions. We actually saw some strange lights on the corner of the sun during that eclipse, and I'm going to have to go online after this and see if there was any cool activity happening on the sun at that time to figure out exactly what was going on there.
Yeah, and just following on that, what do you expect to see when you look at the corona during an eclipse?
So what we just saw here down in Dallas that you're about to see from your view in Carbondale, have a look out for the streamers. These are large pointy things pointing out from what looks like a black hole just sat in the sky. The moon is completely dark, a dark circle, and you see these bright, they're called streamers, pointing out away from it. It reminds me, You know, if you ask a child to draw a star, they'll draw you the 5 or 6 pointed star. That's not what stars look like in the sky. We know this. But during a total solar eclipse, the eclipse in the sky, it really looks like a child's pointing of the star. And that's what you're going to see in just a moment from Carbondale.
And let's just like step out of our solar system, right? Like, what can eclipses tell us about other stars?
Yeah, so at the end of the day, the sun is a star, okay? I'm biased. I research the sun for a living. I'm going to say it's the best star. That will upset a lot of people. But ultimately, it's the star closest to us, and it's the only star in the sky that we can resolve by just a few pixels. So by researching and observing our sun, the atmosphere of our sun, the physics, the eruptions, the flares happening in our sun, we can learn more about all the other stars in the galaxy and even the universe as well, because the sun is just a star. And this has massive implications for cutting-edge science, looking for habitable planets, exoplanets around other stars. Really understanding how those stars work is key to that physics. And eclipses really help us in understanding some of that.
And let me just ask, like, you know, to learn a little bit more about solar physics, what are like current path of research that you might be involved in as an NSO scientist that are current today and that are like key, like hot in the scientific community?
Yeah, excellent question. So I specialize in solar flares specifically. These are large sort of explosions and conversions of energy in the atmosphere of the sun. These produce eruptions into space as well. And so it's my job to understand these eruptions, see how they work, comparing observations to the theories and models. I use telescopes on the ground, such as the Inouye Solar Telescope, telescopes in space as well, whatever observations are available to understand these explosive phenomena.
Hey Ryan, it's Adam in the studio now. So as the non-astronomer on this set right now, I'm really curious to hear your point of view on, you guys have been working on a lot of these experiments and this whole setup for years, if months at the earliest. So it almost kind of feels like a solar physicist like Super Bowl or championship game today. How was the buildup over the past year or two to this point? And then now that Dallas did oblige and open up skies for you to see the eclipse, how are you feeling about the after effect of that?
The atmosphere, electric. I mentioned before, we sent our telescopes north. We were not expecting to see the eclipse here in Dallas. We expected cloud, we expected to see it go dark, but that was about it. 2 weeks ago, looking at this day today, cloud was forecast. Yesterday, looking at today, cloud was forecast. This morning, cloudy. For me, the hype was even better because I had somehow convinced myself that this was not going to happen to us today. And I think a lot of people here felt the same. I think a lot more people would have shown up here to Dallas, here to Texas in general, if the weather forecast had been cleared. But despite the forecast, it's worked out. And for me, you probably saw my reaction there. I don't know how befuddled I looked, but I really was shocked. Even now, my heart is still elevated above resting. And it feels a privilege, to be honest, Adam, to have the world focused on the sun right now. Some of us here, Jorge, myself, we are thinking about the sun all the time. So it feels very special that the sun is in everybody's minds right now.
And before we get to Carbondale, would you like to comment a little bit about the experiment that Kevin Reardon is running there, SuperCade?
So, yeah, Kevin's certainly into a treat. He's got a very big setup of telescopes there. He's got the view of 2 telescopes that you're seeing intermittently coming up on your live stream. These are public outreach telescopes, but he also has a very large telescope that is pointing at the atmosphere of the sun, and he's looking to get measurements of the solar corona. I haven't checked in with the weather up in Carbondale, but the fact that you're seeing the eclipse or the partial eclipse on your screen right now tells me that it's going well. There was a similar setup down in Mazatlan in Mexico. I haven't yet had word of whether or not they were successful, but it'll be interesting to hear afterwards. Here in Dallas, at least, crowds are leaving very quick now that totality is ended. I'm expecting heavy traffic on the road. And following Kevin's experience in just a few minutes, he will also see a mass exodus of people fleeing the areas as well, heading to the highways to try and escape totality, or the traffic from after totality. So I hope Kevin's not expecting to go anywhere in the next few hours because he might struggle.
Let me ask you probably one more. How do you feel about like all these data sets coming together as a solar physicist or someone that is trying to figure out what to do, like going to college and like all these, or a PhD, all these data sets coming together? What does it mean for the solar physics community, like from ground, from space?
Yep. So we're certainly in a very privileged time in solar physics. It is solar maximum. The sun is very active. We have the eclipse today, but we also have a whole fleet of instruments, as you say, on the ground, the Inouye Solar Telescope, here along the eclipse path, up in space, flying through the air. A combination of all of these instruments will come together. Scientists are going to be going over these data for a year, 2 years, maybe longer, but I really look forward to seeing the scientific results that come out from the eclipse that we just happened today. So for anyone at home who saw a partial eclipse from their garden, or anyone who saw the total eclipse, you are witnessing science in the making. You will see scientific publications come out from the event that you have just witnessed, and I think that's a very special thing to consider as well.
And I think we are about a minute away.
Should be approaching totality in Carbondale.
Correct.
We'll go ahead and see if we can show you the two
That's
telescope setup that Kevin Reardon has.
So we're just witnessing the final fleeting moments of sunlight up in Carbondale. You can see the tiny slither of the sun there. Wow, just look how thin that slice of the sun is. You can even see some texture there along the bottom left. And we're switching views here on the left. They have taken off their solar filter, and we're now about to see, if all goes well, the atmosphere of the sun. The final sunlight fleeting. Take a look at the sunlight shine through these final craters on the moon here. They're called Bailey's beads, these small bead-like structures. Yeah, that's very cool. And what we're about to see, hopefully, are some structures coming up around the edge of the moon. And this is the lower solar atmosphere. We call this the chromosphere. And there you can see them there. These small blobs around the outside, the small brighter blobs right near the edge of the moon, that is the lower solar atmosphere. And this wider view that you can see is green right now. That is the corona of the sun. That is the atmosphere of the sun right there. And the thing about the corona is it's very structured. We can't quite see in this view, but with a wider view, which we experience here in Dallas, you can see these structures span multiple times the size of the moon and the sun itself in the sky. But here we're looking at the lower atmosphere of the sun, and you can see a lot of detail there. Really nice. I wonder if the other telescope is giving us anything at the moment. Oh, that's interesting there. You can see on the right, you can see those bright blobs I was talking about. That is low. That's really cool. They are structures very low in the atmosphere of the sun that are just poking up above the edge of the moon. That's the chromosphere, and you might even be able to see they have a sort of a reddish glow. This truly is magical. I look at the atmosphere of the sun all day from telescopes from in space and on the ground, so actually seeing this with my eyes, this is definitely something everybody should strive to do at some point in their life. The next eclipse coming up in the United States is not for a little while. There's one in Alaska in 2033, but the next times you'll see that in sort of the main lower 48 states, back to back in 2024 and 2025. But you don't necessarily have to wait that long. There are other eclipses happening elsewhere in the world. The next eclipse coming up is in Greenland, Iceland, and Spain. And that will be on the August 12th, 2026. So just under a couple of 2.5 years from now, just under. The day before my birthday, funnily enough. So I'll definitely be celebrating that one. And looking at this telescope view here, just looking at the right, you can see that bright structure just peeking over the very edge of the moon on the right-hand side there. We saw that with our eyes. I mentioned earlier that I'd seen something on the sun and I wasn't quite sure what it was. I wasn't looking magnified, so I couldn't quite tell. That appears to be some sort of prominence up above the edge of the sun there. And we saw that with our eyes here in Dallas as well. Take a look also at the outside of the moon. You can see it's not a perfect circle. You can see some ridges and bumps around the outside there. So we're starting to see the very top right now. You can really see another bright structure. I actually wonder if the top right is probably where we had been looking actually down here. They'll be coming out of totality very shortly. About 20, 30 seconds or so. So you're going to see sunlight start to shine again from the top right of the sun. There we go, look at that. And the sun is back, and you can see how quickly the brightness of the sun overwhelms the emission from the corona, or the sun's atmosphere. Wow, so there we go. I think that is totality from Illinois. We'll probably have another view back from the other telescope shortly, but I will pass you now back to the studio.
Thank you, Ryan. Appreciate it. Thank you for camping out down there in Dallas, even with the threat of possibly not being able to see the eclipse today. So we sincerely appreciate that. So for all of us, thank you guys for joining us. That will conclude our 2024 total solar eclipse coverage. From the National Science Foundation, I'm Adam Eggers.
And from NSO, I am Jorge Pérez Gallego. Thank you all very much for watching. Muchas gracias.
Thank you, guys.